Okay, Ohanian 6.66 tells you that you have a car of mass equals 1,200 kilograms traveling at a speed of 25 meters per second around a track of radius 400 meters. Okay, but the track isn't flat, it is banked at an angle theta equals 6 degrees. And the question is, can you find the normal force and the friction force acting on that car so it doesn't fly up or down the bank? Okay, so we'll get started by drawing a free body diagram. Pull out my trusty ruler. I'll draw an angle bigger than 60 degrees because it'll make it easier to see things, but I'll be working the problem in terms of variables, in any case theta, only plugging in numbers at the last moment. I'll draw the car as a little square, but you can just draw it as a point if you want. Okay, and it has a mass m, so there's a force mg down. There's a force perpendicular to the road, that's the normal force, and there's a force of friction along the road. Now I don't actually know whether this force of friction points up the bank, and that would be the case if the car is traveling slowly enough that it's tending to slide down and friction is preventing that. But if the car is traveling so fast that it's tending to fly off the top of the bank, then the force of friction is in the opposite direction. Now, it might seem like you have to work the problem both ways, and sometimes you do, but because you're given the information about the acceleration, you know v squared and you know r, it turns out that that's already determined. I just don't know what it is, but I can arbitrarily pick the force of friction going up in this direction, and if I'm wrong, then I'll just get a negative sign for the force, and there won't be any problems other than that. Okay, the other things I need to do is I know I have to pick a coordinate system. I know the acceleration. Now, this is not really the free body diagram, but the acceleration equals v squared over r towards the center of the circle, so it points horizontally. So it would be wise to pick a coordinate system that is horizontal and vertical rather than aligned with the track. And I'll pick my positive direction towards the center because I know my acceleration's in that direction, and my positive y pointing up. Now the other thing I need to do is to break down all of my forces into components along these x hat and y hat directions. Well, mg is already in the y hat or negative y hat direction. I have to do this for the normal force and the frictional force too. And to me, the easiest way to do that is to draw another diagram, like so, with the same angle theta there. Realize the normal force points perpendicular to this track, so it points in this direction. That's a right angle. Okay, and that's my normal force. And now I can start drawing other angles, triangles, that will help me sort out what the components are. So if this angle is theta, and this angle is 90 degrees, then this angle is 90 minus theta, so this angle is theta. So that tells me that the opposite side, my nx component, will be n sine theta. And likewise, the vertical component will be n cosine theta. And both of those are my positive x hat and positive y hat directions. And now I'll do something similar for my frictional force, which is not along the coordinate system axis. So I'll draw another triangle with an angle theta. But now I recognize that the force of friction is in this direction. And I have to break this up into components along and perpendicular to my coordinate system. Well, that's just this direction and that direction, x hat and y hat. So the force, this should be force of friction, sorry. The force of friction in the x direction is just the force of friction cosine theta. And the force of friction in the y direction is the force of friction sine theta. So now I have all the components I need and I'm ready to work. I'll notice that in my choice of force of friction, this is a negative component and that's a positive component for the force of friction. So the next step then is just to write down Newton's second law for the two coordinate directions. The sums of the forces in the x direction. Well, I've got a normal force component n sine theta here in the x direction, pointing in my positive x direction. And I've got a component of friction minus force of friction cosine theta. That's this component in my negative direction, which is why I wrote negative. Those have to sum to the mass times the acceleration in the x direction, and that's just v squared over r. Okay. And then I write down my Newton's second law equation for the forces in the y direction. And that's a component of n and cosine theta, which I see by looking up here, and cosine theta. And that's a component of, well, all of gravity actually, because mg points straight down in my negative y direction. And I also have a force of friction, but that's positive for my choice of direction. So plus the force of friction sine theta equals 0. So I have two equations, and I've got two unknowns, n and the force of friction I'm trying to solve for. Everything else, theta, m, g, are given you, v squared or v and r, are given you. So now it's a question of doing the algebra. And there are lots of ways to solve this for n and f, and there may be better ways than the one I'm about to show you. When I look at this, I say, well, I think I'll go and eliminate n first and see what the force of friction is. Okay, so I can do that by multiplying this equation by sine theta over cosine theta to change this to n sine theta, then subtract it from this equation. That will eliminate n. So all I'm going to do is take my sum of the forces in the y direction equation, multiply it by negative sine theta over cosine theta. Okay, that will give me an equation that's, instead of this, it will be equal to negative n sine theta, then multiply mg times this, and that will be plus mg sine theta over cosine theta. And then do the same thing here, and I'll have minus the force of friction sine squared theta, okay, divided by cosine theta, and all this equals 0. Now I want to add this to this equation, so the n term cancels out, which is what I was trying to do, and I'm left with mg, okay, mg sine theta over cosine theta. Well, that's just tangent theta, so I'll write it as tangent theta. Okay. Then I have minus ff times cosine theta plus this term, so that is equal to minus the force of friction, which appears in both of them. And then I've got a cosine theta, well, a sine squared theta divided by cosine theta plus a cosine theta, because I have a minus out in front. And those have to be equal to mv squared over r. That's just 0 plus mv squared over r. So now I have an expression here that I look at and I realize, hey, I can simplify this expression in brackets. If I just add those together, that'll be sine squared cosine squared theta, okay, plus, to make this cosine theta over cosine theta, that's plus cos squared theta. And I remember from high school that that's equal to 1. So this expression reduces to 1 over cosine theta. Nice simplification. So let me rewrite what I've got here. I've got mg times tangent theta minus the force of friction, 1 over cosine theta, equals mv squared over r. And I can rewrite this to solve for the force of friction. The force of friction, then, I'll just take this over to that side basically, but then flip it again. So I'll have to multiply through by cosine theta. So I'll have that's equal to mg. Now tan theta times cosine theta, remember tan theta is, well, I'll just write it out for you. Tangent theta times cosine theta. And that'll then it'll be minus, sorry, because this will be on the other side, minus mv squared over r cosine theta. But tangent theta is sine over cosine times cosine. This whole thing becomes sine of theta. Okay, so I'm left with f equals mg sine theta minus mv squared over r cosine theta. And at this point, I could just plug in all the numbers that I'm given. 1,200 kilograms, 9.81 meters per second squared, 6 degrees, etc. Plugging in the velocity, 25 meters per second squared. Okay, so I won't work through all the plugins on my calculator here on the paper. I just tell you the result is minus 634 newtons, although depending upon how you handle significant figures, etc., you might find 630 or 640, and hopefully the graders won't take off points for that. I've told them not to. So that's my answer for the force of friction. Okay. Once I've got, oh, by the way, negative sign. The fact I have a negative sign here means I chose wrong there, but it's not a mistake. It just means that the force of friction is actually pointing in the other direction. The car was trying to fly off the track. It was held on by the force of friction. You're also asked for the normal force, and you have a few ways to do that. Looking at these two equations, I can use either one. I'll just go ahead and pick the F of the sum of the forces in the y direction equation to avoid v squared over r. And so I can write from the sums of the forces in the y direction, I can solve that for n. N equals mg minus the force of friction sine theta. We divide it by cosine theta. Just solving this equation for n, putting these two terms on the other side, dividing by cosine theta. Again, all you have to do at this point is plug in the numbers for the mass, g, etc. You're given all of them. And if you do that, you should find that the normal force is about 1.18 times 10 to the 4th newtons. Done. Now notice, though, that this is the opposite order from what you were asked, but that's okay. If I'd wanted to, I could have instead eliminated force of friction instead of the normal force here. Again, that was arbitrary, and you could do it either way.